Swayam Prabha. Digital India. Educated India.
Hello, welcome to Basics of FEA Part 1. This is a 8-week course. Each course we will have 6 modules, one module on each day, Monday, Tuesday, Wednesday, Thursday and Friday. So overall we will have something like 48 lectures. Each lecture will be something like 20 to 25 minutes. And then at the end of each lecture we will also have an assignment which you will be expected to do. Most of these assignments will have multiple choice questions. So please do those questions. Even though they are multiple choice, to answer those questions you will have to have some good understanding of the theory of finite element analysis. So it is important that you listen to these lectures carefully and work accordingly. The book which I will be heavily relying on for this particular course is Introduction to the Finite Element Method, and the author of this book is J.N. Reddy. It's a very popular book, and the strength of this book is that it's extremely easy to understand. Finite element analysis or finite element method is a technique to solve differential equations, and it's mathematically very intensive. So a lot of books in area of finite element method, you will see that they are extremely heavy on mathematics, and in that process sometimes the understanding part of the book through its language and through explanations is not that clear. So the advantage of the book by J.N. Reddy is that it's easy to understand, and yet it does not compromise on the mathematics of the course. So that is the book I will be referring to, and then of course we will have examinations, mid-semester examinations and also end-sem exams, and that's how we are going to do. In this particular, so this is part 1 of the course, these 8 weeks. And then maybe in July onwards we will have a new set of MOOCs. So then in that particular course I will do the second part of finite element analysis. What you will learn in this first part will be basically the theory of finite element method as applied to one-dimensional problems. And so you will understand how complex geometries are broken, how they are discretized, how are assembly element level equations written, how are assemblies done, a lot of stuff about terminology, how do you apply boundary conditions, what are initial value conditions, what are boundary value conditions, what are the different mathematical approaches for this. And I think if you have a good understanding of 1D type of problems, then going from there to 2D type of problems is relatively easy. That's not a big jump. So most of the conceptual understanding in context of finite element analysis, it starts right away from 1D problems. So we do not have to think that 1D problems are simple, 2D problems are complex, and 3D problems are super complex. If you get a good understanding of 1D, then going from 1D to 2D, the only additional step is how do you assemble elements in two-dimensional systems. And then from 2 dimension to 3 dimensions, actually that transition is fairly straightforward because there is nothing new when you go to 3 dimensions. So that is, so even if you are planning to do the part 2 of the course, which will be after June or July, if the plan goes correctly, then having a good grip on that particular course will very strongly depend on how we treat the subject at this level. So that is the prelude. So once again, I welcome all of you to this particular course, and I hope that you enjoy this course and learn something worthwhile and useful, because finite element analysis is now very extensively used in almost all areas of science and technology and engineering. So you can be a mechanical engineer or a civil engineer or an aerospace engineer, you can be a material scientist, you can be a physicist, you can be a chemical engineer, and virtually all areas of engineering and science in some form or other FEA is used, because what FEA allows you to do is to solve complicated differential equations. You know that suppose you have a function, you can have any function, and differentiating any function is a pretty straightforward process. But integrating any function, any general function, is not that straightforward, because the way we have defined integration or integral of a function is we actually consider it as an inverse process of a derivative. So suppose you have x square and I want to integrate it with respect to dx, then the way I do it is that I know that derivative of dx, derivative of x cube is 3x square. So then what I do is I know this information. So I know that the derivative of cubic of x is 3x square. So I say that, okay, if that is the case, then antiderivative of 3x square is x cube, and from here I infer that integral of this will be x cube over 3. Okay. So what this basic concept means is that if I have to integrate a function, I have to basically, I am trying to find its antiderivative, which means that I have to figure out a function whose derivative is this thing, and finding out that function is not a straightforward affair. But if I want to differentiate any function, that is pretty straightforward. So the point what I am trying to make is that when we have differential equations which actually capture several physical phenomena, for instance, if there is a heat transfer happening across a body, then the way you capture the physics of that body is through a differential equation. You have a body, suppose this is a body and I am putting some force on it, and I want to calculate stresses and strains in this body. Then again I have to write equations of equilibrium in differential form. So again I have a partial set of partial differential equations which govern that phenomena, and each time I have partial differential equations or ordinary differential equations, I have to solve for unknown variables. For instance, if I am trying to bend this pen, the unknowns may be displacements in the pen at different points in space, and so those are the unknowns, and the way I solve for those unknowns is I have to integrate the partial differential equation which governs the bending phenomena of a pen. And as I explained, in general, integration is a much more difficult and complex, non-straightforward process than differentiation. So finding integrals of partial differential equations or ordinary differential equations, in some cases it is easy and straightforward. In most of the cases, it is not easy and not straightforward. So finding exact integrals of complex functions is not straightforward. So then what we do is that we try to solve these equations not in an exact sense, but in an approximate sense. Okay. So we will say, okay, we are okay if my solution is not 100% accurate, but maybe 99% accurate. So we use some approximate methods to solve or to integrate these equations, and that is where techniques like finite element method come into picture. Okay. So I will give you some couple of comments on finite element method. So So, the first thing is that this method helps us numerically integrate, and we will explain this term numerically as we walk through this course. Integrate, or I can also call it solve differential equations. Now, these equations could be PDEs, partial differential equations, or they could be ordinary differential equations, does not matter. These equations could also be linear or non-linear, it again does not matter. A very big advantage of finite element analysis is that it is very general, and because it is general, it is also very flexible. What do I mean by that? So, if you have a particular ordinary differential equation or a PDE, you can integrate it under some special conditions. There are several ways, right? You have this variable severable method and so on and so forth. So, there are several methods, but each method of integrating a partial differential equation is applicable to only a limited set of conditions. Okay? It is only applicable to a limited set of conditions. But when we start using techniques like finite element method, this method is more or less insensitive to the type or form of the partial differential equation, because the philosophy it uses, and you will see it as we walk through in detail, the philosophy on which it rests on is very generic. So, it does not matter whether the solution is of equation is of this type or some other type, whether it is homogeneous or non-homogeneous. If we understand the overall theory of finite element method reasonably well, then we should be able to solve or integrate these equations which define or capture the essence of several physical processes fairly with a fair amount of accuracy and reasonableness. So, this is very general, and because it is general, I can use the same method to solve a heat conduction problem, I can use the same method to solve a thermal diffusion problem, I can use the same method to solve a problem in computational fluid dynamics, or do stress analysis, or do dynamics, or understand vibrations, or understand the physics of the universe, and so on and so forth. So, because it is general, it is also very flexible. And another advantage is that it is highly systematic. It is highly systematic and structured process. What does that mean? So, a lot of times when we try to solve differential equations, we make guesses, right? We guess a solution and then we try that solution by plugging it back into the equation and see whether the equation is satisfied or not. It gets satisfied or not. This type of a process where you have to guess, or you have to intuitively figure out the solution of a differential equation, this type of a process cannot be easily implemented in computers, because a computer cannot guess solutions. Okay? In context of FEA, we do not rely on this intuition, but the method is very systematic, very structured, and there is a very well defined algorithm which drives the whole approach. So, if you have a very systematic and structured process, then you can easily automate it. So, it is easy to automate it, and as a consequence you have a problem and you have a very generic code. That generic code for stress analysis can solve how a pen bends, or how if I am stretching this strap of this watch, how does it deform, or if I am bending this plate and it is deforming. So, the same code, the same software is able to solve a very large number of problems, and the variety of problems it can address is not limited by size or shape or material properties or things like that. So, it is easy to automate because it is highly systematic and it is a very structured process. and as a consequence of these things that it is very general, and also because it is highly systematic and structured process, it is used almost in all areas of science and technology. So, okay. So, that is there. So, now what we will talk maybe over next 5-7 minutes is give you a very basic overview. Again, this will not make you experts in finite element method, but it will give you a very basic overview of what is the overall philosophy of finite element method. So, the first step when you are trying to use finite element method, so let us say that I have a, let us say this is a beam and I am trying to bend it, okay. I am trying to bend it, and I have to understand how this, when I apply a force F on this beam, and let us say the beam is rigidly fixed here and I am applying a force here, this beam is trying to bend, and when it is trying to bend, I have to figure out that at each point along the beam, what is the displacement in x direction, in y direction, and in z direction, and whatever. So, and I want to, let us say, solve it using the finite element method. So, the first process, the first step in this entire process is that we develop a set of governing equations. This step is invariant in the sense that whether you are trying to solve the partial differential equation in an exact sense by directly integrating it, or you are trying to use finite element method to solve the thing, this step has to be there. So, you have to develop a set of governing equations. For instance, in this case of the beam, what is it that we are trying to do? We are applying a force, and as a consequence of this force, this structure is bending. So, what I am trying to develop is a set of equilibrium equations, because there is mass here, there is stiffness, there are forces, and our laws of Newton tell us that this thing will bend and move only if external forces on each small element of this material is not 0. So, I take a small piece of material, I see what are all the forces on it, and then I develop an equilibrium equation for this. So, that is one thing. Then using laws of geometry, I try to figure out what is the relationship between the curvature of the beam and the displacements in the beam. So, first set, and at least in context of this beam, first set of equations would be equilibrium equations. Second set of equations would be strain displacement relations. Okay. So, equilibrium equations are basically statements of Newton's laws of motion. Strain displacement relations, they are basically driven by geometry. Okay. And the third set of equations will be how stresses and strains are related. Stress strain relationships. Now, these set of governing equations are applicable to, let us say, solid mechanics. Okay. But if our problem is different, say it involves heat transfer, then these set of equations will differ, and we have to develop a different set of equations which are applicable to the heat transfer process. But regardless, we always start by developing a set of governing equations. Once we have done this, then what do? We solve these governing equations. So, we solve these. And before I go deeper into how we solve these equations using finite element method, we will see we will have a very quick overview in terms of what are different types of methods to solve these equations. So, the first way to solve them is exact solutions. Okay. So, one way we can solve is we get an exact solution of these differential equations. So, what is the meaning of exact solution? It means that my solution has to do two things. It has to A, satisfy governing equations exactly. It has to satisfy and at all points in area of interest. Okay. So, that is the first thing, that whatever solution I have, suppose I get a solution that displacement equals Ax plus Bx square plus Cx cube plus Dx4 and so on and so forth. This solution, if I plug it back into my original differential equation, then the left side of the equation and the right side of the equation, they have to match exactly for all values of x which lie in my area of interest. Okay. So, that is the first condition. That is the first condition. The second condition for an exact solution is that all the boundary conditions are exactly satisfied. Okay. So, there could be a situation that the differential equation is exactly satisfied, but the boundary conditions are not. In that case, the solution may not be exact. There could be another situation where some boundary conditions are satisfied and some at some points the differential equation is satisfied, but all boundary conditions are not satisfied or whatever. So, all the boundary conditions have to be satisfied, and the second one is that the governing differential equations which we are interested in, they have to be satisfied at all the points. So, suppose I say that my displacement, suppose I guess that the displacement in this vertical direction, if I apply a force, is C1x plus C2x square plus C3x cube plus C4x, then at all the points in the beam, that equation has to satisfy the governing differential equation which supervises or oversees the behavior of the beam at all the points. So, that is there. Now, so if the solution is exact, then our error will be 0. Okay. The other thing, so that is the first set of solutions, but then in most of the cases, unless our problem is very simple, these exact solutions are not possible. So, then we go for approximate solutions. Okay. And there are, broadly speaking, two categories of approximate solutions. First one is analytical solutions, and then other one is numerical solutions. Now, in approximate, in exact solution, the error, and what is the error? The difference, if you have a governing differential equation, the difference between right hand side and the left hand side, that difference will be always 0. If the difference is not 0, then that is regarded as the error. Okay, that is defined as the error of the solution. In exact solution, for all points, the error is 0. In approximate points, the error is not 0 at most of the points. But what we say is that in this case, one way what we try to do is that we will say, okay, if I have an error, okay, and I multiply it by some weighting function, by some function. At this point of time, we will just call it some function, some weighting function. We assign it some weight and we integrate it. And suppose the beam, if it is a beam, then we integrate it over the length of the beam. Then the weighted integral of the error is 0. This is one strategy to achieve an approximate solution. So, point by point, the error may not be 0, but error may be a little bit high at one point, a little bit low at one point, and if you add up all these errors after weighting, then that is the integral, right? That is the integral. So this is omega. It represents domain. What domain means? The area of interest, the region of interest. So if I integrate this error in a weighted sort of way, and I will use this term weighted again and again, and slowly it will become more and more clear to you what it means. In a weighted sort of way, if I integrate this error over the domain, which means the region of interest, then that error is going to be 0. Okay. So then these approximate solutions, they lie in two categories, numerical and analytical. And in analytical solutions, we get, in plain language, we get some formulas as solutions. Okay, we get some sort of formulas. So maybe the deflection will be some sort of a series expansion, or it may be a polynomial expansion, a series, or a sinusoid, this harmonic series, or some sort, or an exponential series. So there will be some relationship between some formulaic relationship for the unknown variables in which we are interested in. In numerical solutions, we don't get formulas, but we get numerical values at different points in the region of interest, that is the domain. In domain, and once again, what by domain I mean the region of interest in which I am trying to find the solution. Okay. So suppose I have this piece and I am applying some force here. If I apply a force here, and if I am trying to develop an analytical solution, I will get some sort of, I will have to develop some sort of function which will explain or which will define how u, v, w, suppose displacements is what I am interested in, how v, u, v, w are changing with respect to x, y, z in this cone. But if I am using a numerical solution, then I will not have this kind of a formula, but rather I will have maybe at this point the stress is 3.1, at this point displacement is 2.7, so I will get numerical values. So the finite element method is a numerical approach. It is a numerical approach. Another approach which is numerical in nature. So two approaches are popular. One is FEA, other approach is boundary element method or FEM. It is also called analysis, and the third one is finite difference method. These are three methods. Okay. One more thing. So we can do approximate solutions either using this approach. So we said that approximate solutions, in approximate solutions there are two categories, analytical and numerical, and in both these approaches what we are trying to do is we are trying to have a weighted integral of the, we weight the error and we do a weighted integral of the error, we add that up over the domain and then we equate it to 0. So that is what we do. We will learn what this weighted integral is later, so you have to be patient, but that is what we are doing. Another way to do approximate solutions is to define, so this is method 1. This is method 1. The other method, method 2, is known as finite difference method. So actually I should erase FDM from here, and here we do not do the weighted, we do not calculate the weighted integral of the overall system. Rather what we do is that we express derivatives as differences. Okay. So suppose I have to calculate del u over del x, then what we do is we calculate the value of u at point 1 at x is equal to x1, you calculate the value of u at another point where x is equal to x2, and then we say okay, the partial derivative of u is u2 minus u1 divided by x2 minus x1. So once we do that, we very rapidly convert these partial differential equations into algebraic equations, and then we can solve those. So that is another approach. So we have an integral approach, this is method 1. We have another one, method 2, finite difference method. In method 1, we can have analytical solutions or numerical solutions. Method 2 is finite difference method, and that is only a numerical method. So this completes our first module, and we will again meet tomorrow for the next lecture. Thanks.